Hello and welcome to Week 5 in Database Systems. Our agenda is to go over first the assignments, and then we'll talk about chapters 12 and chapters 13. First, the assignments. During Week 5, you're to read chapters 12, which deals with object-oriented and object-relational databases, and then also chapter 13, which centers on XML, which is Extensible Markup Language. Also, discussions for the first discussion for week 5 should center on chapter 12, where you will talk about object and object relational databases. That is due by the end of the week at midnight. And then the second discussion is centered on chapter 13, which deals with XML, also due at the end of this week, week 5. And then lastly, the course project phase 2 should be on your radar, though it is due at the end of week 9. So is a good time to start looking at it and planning for it. So week 5's objectives is, first of all, in chapter 12, we're going to talk about object-oriented database concepts. We'll talk about object relational features. We'll talk about object database extensions to XML or to SQL. And then we'll talk about ODMG, which is the object modeling and the object definition language of ODL, object database conceptual design, and then object query language, OQL, and then lastly an overview of the C++ language bindings. And then chapter 13 will center on XML data modeling and languages. For the first discussion, which is around chapter 12, you should talk about inheritance in the ER model, chapter 4, and compare that to the inheritance in the object-oriented model described in section 12.1.5. Make sure that you respond to that prompt with 250 to 300 words, including at least one citation. That is due the initial post by Wednesday at midnight. Then by the end of the week, ensure that you've responded to 2 of your classmates in a constructive way, building on the conversation. The second discussion is about chapter 13, where you're asked, what is the differences between structured, semi-structured, and unstructured data? Respond to that prompt with 250 to 300 words. Make sure that you do that by the end of day on Wednesday. And then the following, by the end of the week, make sure that you responded to 2 of your classmates' posts. Regarding the course project, the second phase of it, you should produce an ER model for the following scenario presented in step 1 below, and business need for the Math Academy. Reference the attached video, course project phase 2 video, for a full introduction demonstration of the expectations of this project. The deliverables include an ER model for the scenario presented. You have the option to use either Visio or use ER model. Alternatively, if you do not have Visio, or I'm sorry, you have the option to use Visio to produce your ER model. If for some reason you don't have Visio, you have the choice of using ERD Plus, which is an open source ER modeling software that's available online. Either is acceptable, but you do need to produce your diagram using one or the other. The following are the steps for the phase 1 of the project. The first step is to read and understand the scenario and business needs presented, define and document the entities and relations required to address the business needs. The nouns in the scenario below will give you the entities that you're going to need, and basically the verbs will be the relations. So the scenario and business need. The Math Academy is in need to develop a database to track and control of its students, teachers, and classes that are offered. Teachers are able to teach multiple courses, but they are required to be certified on the course while they are teaching. For example, only groups of teachers are certified to teach algebra, and another group is certified to teach geometry. Students can take multiple courses. Courses are taught by teachers with the proper certifications and have multiple certs as needed. Courses are taught in one of the classrooms at the school's several sites. Each classroom is optimized to serve the needs of a course. For example, some courses might require computer labs and whiteboards. The school needs to keep track of the math courses delivered in each of the sites. The second step is for this project requires you to use Visio or ERD Plus to produce the deliverables. If you're using Visio, follow the following steps. Reference the course project phase 2 video for a short demonstration and tutorial of this tool, and project overview and expectations. You open Visio, you'll click on Software Database Templates in the main window. Select the database model diagram template to open a new file. Save the file and ensure to have in your file name project2 underscore your last name and then your first initial. If you're using ERD Plus, watch the recorded short video for this tool. Reference the attached video as follows. From the ERP Plus main interface, select Documents, New Diagram, name your diagram, ER diagram, and then create. Reference demonstration videos for how to navigate the tool, how to create entities and attributes, relationships, and cardinality. Demonstrate videos as follows. Step 3, define the database and entities. Add an entry for each table you identify in the scenario and business needs. You will use the MS tool, Visio tool, or the ER Plus open source software offering to complete this step. Add the required entity attributes. Add the required attributes for each entity that you feel would be necessary essentially for that particular entity. Select one of the attributes to be the primary key. Define the relations. Use the crow's feet notation. Reference recorded demonstrations on how to use these notations for MS Visio in ERD Plus. Reference attached videos as follows. Drag and drop relations between the entities you defined. Connect the ends of the two entities for each relation. Define the primary key for the parent entity. The fifth step is to define the relationships. Use the crow's feet notation. And then for the sixth step, define the cardinality relation. Set the cardinality for each of your relations as defined in step 5. For MS Video, select a relationship line in the drawing area that is connecting two entities. In the database properties window, select the miscellaneous category, select the cardinality for the selected relationship. Step 7 is to upload your work and submit it for review. The course project rubric, 40% is based upon the ER model. 40% is off of, or 40 points is off of the entities, 40 is off of attributes, 40 is off of relations, and then another 40 off of cardinality for a total of 200 points. Chapter 12 centers on object and object relation databases. So the objectives that we're going to go over is as follows. We'll review an overview of the object database concepts. We'll talk about object relational features, object database extensions to SQL, ODMG and object model, and the object definition language, ODL, the object database conceptual design, and the object query language, OQL, and then an overview of C++ language binding. Object and object relational databases. Object databases, ODBs, are a type of object data management system, so ODMS. They meet some of the needs of more complex applications. Specifically, they allow you to structure complex objects and operations that can be applied to those objects. Introduction to object-oriented concepts and features, the origins of object-oriented programming. Object has two basic components. It has states and behaviors. So you essentially have values, and then you have things that can interact upon those values. You have an instance variable. Those are attributes that hold values that define internal state of the object. Operation is defined in two parts. One is the signature, which is essentially the interface. The second is the implementation, which is the method which implements the interface. Inheritance is the concept that allows you to, it permits the specification of new types or classes that inherit much of their structure and or operation from previously defined types or classes. Operator overloading is the concept of having one operator that has the ability to be applied to different types of objects. Operation name may refer to several distinct implementations. Object has a unique identity implemented via a unique system-generated object identifier, so an OID. And generally speaking, objects are immutable. At least the unique identifier is. Most object-oriented database systems allow for the representation of both objects and literals, simple or complex values. The complex type structures for objects and literals. The structure for arbitrary is of arbitrary complexity. It contains all the necessary information that describes objects or literals. Nesting type constructs generate complex types from other types, type constructors, type generators. You have atomic or an atom, which is a basic data type such as an int, string, or etc. A struct or tuple, which is a bit more complex, typically made up of either structs or atoms. And then you have collections, which there can be kind of a variation and combination of these various things together. A collection is essentially something that stores other things, simplest being something like an array, could be a dictionary or an associative array, a list, any number of ways of containing things. Collection types include things like sets, bags, lists, arrays, and dictionaries. Object definition language is used to define object types for a particular database application. Figure 12.1 is an example of specifying the object types for an employee, date, and department using type constructors. Encapsulation of operations. Encapsulation is related to abstract data types. It defines a behavior of a class object based upon operations that can be externally applied. External users are only aware of the interface of the operations. Can be divided structurally between objects into visible and hidden attributes. So basically, the idea is that you have an interface, a specification of how you're going to talk to something, but you don't necessarily know about the internal implementations of that interface. Encapsulation of operations, you have a constructor operation. This is used whenever an object is being created to initialize the state to some anticipated or desired state, and oftentimes supplied with parameters. A destructor operator is something that is used to destroy or delete an object, to clean up or whatever it might be. A modifier operation is something that modifies the state of an object or changes it in some way. So it's essentially something that allows for manipulation of the values associated with the various fields within the object. A retrieve operation and a dot notation to apply operations to an object. Transient objects exist in execution. Whenever a program is executing, they disappear once a program terminates. Persistent objects are those which are stored in a database and persist after object termination. Naming mechanism assigns an object, is assigned a unique name in the database. The user finds that object by that name. Reachability refers to ability of an object to be referenced from another or from other persistent objects, object location through the references. So basically you can reach it by starting with some other objects that have been persisted. Figure 12.3 contains the process of creating persistent objects by naming and reachability. A type or a class of hierarchies and inheritance. Inheritance it's basically the definition of new types based upon other predefined types, leads to type or class hierarchy, type name and list of visible public functions, attributes, or operations. The format is type name : function, function, function. The basic idea here is that you're defining a particular behavior or instance of or type of an object based upon ones that you have previously defined. The idea here is that there is some behavior that is perhaps shared amongst multiple types of things. You want to define it on the base type and then have the derived types be able to either extend it or augment it or utilize common functionality without having to re-implement it. And the basic driver of all that is software reuse, code reuse, to minimize the creation of new things. A subtype is useful whenever creating a new type that is similar but not identical to an already defined type. That is that new thing that you're creating based upon something else. A subtype inherits functions, additional local or specific functions in the subtype. An example is an employee is a subtype of a person. They have a salary, a hire date, and a seniority. A student is a subtype of a person that has a major and a GPA, and likely a person has something like a name and maybe some identifying capability, maybe a social. An extent, a named persistent object to hold a collection of all persistent objects for a class. A persistent collection is stored permanently in the database. Transient collection exists temporarily during the execution of the program and then goes away once the program terminates. Polymorphism of operations is also known as operator overloading. The idea is that one method may do different things depending upon what it's associated with. Allows some operator name or symbol to be bound to two or more different implementations. Types of objects determines which operator is being applied. You have multiple inheritance. This is where a subtype inherits functions, attributes, and operations from more than one supertype. Not every language allows such things, or databases allow such things. Sometimes they restrict you to single inheritance because it gets complex if you do multiple. A summary of the object database concepts. You have this concept of an object identity, some way of finding that object in a unique way. Type constructors, these are type generators. Encapsulation of operations, programming language compatibility, type and class hierarchies and inheritance, extents and polymorphism and operator overloading. Chapter 13 centers on XML, which is extensible markup language. Database functions as data sources for web applications. So generally speaking, whenever you have a web page, the information that's coming out of that page, unless it's truly trivial, is oftentimes coming out of a database. Sometimes these web applications use static HTML. You may have something that's XML or JSON. It's a self-describing document that lends itself to dynamic web pages. The chapter focus here is on XML data modeling and languages. Section 13.1 is about structured, semi-structured, and unstructured data. Structured data is stored in relational databases. It's something that is very rigid, has a predefined schema, and you are expecting things to be of a certain type and size. Semi-structured data is not all data has identical structure. Schema is information is mixed in, somewhat self-describing, typically some form of directed graph model. Unstructured data has little to no data type indication. Examples of that is just plain text, maybe a web page that's in simple HTML, but more likely think Facebook post or something, or Twitter tweet. This is an example of a semi-structured data as a graph. You have company projects. Underneath of that, you have various projects. Projects have names, numbers, locations, and so on, which are essentially attributes. HTML uses predefined tags. There's generally a document header, a script, functions, formatting styles, maybe it's including some styles and whatever it might be. Then there's a body, then there's which is typically made up of a set of tags. You may have table tags, various other types of tags, attributes associated with those tags, and a large number of predefined tags. XHTML extends the tags for different application and enforces the fact that the document must be a valid or well-formed XML document, meaning that all opening tags must have corresponding closing tags, or they must be done in line. Basic objects, an XML document has an element, it's simple, complex, or a schema document that defines element names and attributes. A document type, typically they're data-centric, document-centric, or hybrid. The conditions of an XML document being well-formed: it begins with an XML declaration. There's a special tag that has to begin at the very beginning of the document. It is syntactically correct, and it is meaning that all of the opening tags have closing tags and so on. It adheres to the specification of XML, and that it is valid, meaning that it follows a schema if one is specified. The notation for specifying elements: element name star indicates an optional multi-valued repeating element. Element plus indicates a required multi-value repeating, so it must have at least one. A question mark indicates an optional single valued, so it may have 0 or 1. And an element name indicates a required single value non-repeating element. The notation for specifying elements: the type specification by parentheses followed by the element name. the exclamation @ list used to specify the attributes within the element. Parentheses can be nested when specifying elements. The bar symbol indicates either E1 or E2 can appear in the document. This is an example of a DTD, a document definition, essentially document type definition that is, or doc type basically definition, that it tells you what the schema is for, or the expectation of a document to be considered valid, that deals with projects and it looks like locations perhaps. XML schema language is somewhat similar, but it's implemented a little differently. Structure, it specifies the document structure, same syntax rules as XML documents. Elements, attributes, keys, references, and identifiers are included. And an example is 13.5 in the text. The XML namespace defines a set of commands that can be used, kind of like a scope or similar to a namespace in coding the world. Annotations, documentation, and languages used. Elements and types. There's a root element followed by multiple first level elements, potentially multiple, and then specifying element type, min and max occurrences. Keys are constraints that correspond to relational databases. There's a primary and foreign key. You can have complex element types with XSD, complex type, and composite compound attributes. Section 13.4 is about storing and extracting XML documents from a database. Use the file system or DBMS to store documents as text. That's one choice. Use DBMS to store document contents as data elements. Design specified systems to store XML data, or create or publish custom XML documents for pre-existing relational databases. XML languages, query languages and standards include XPath and XQuery. Specifying XPath expressions in XML returns a sequence of items specifying certain patterns, values, elements, attributes. Qualifier conditions, separators, slash, double slash, those are going to control if you're looking underneath of one or looking through the entire document. XPath and XQuery are highly used if you do much with XML, so you can't really do it without using it. Here's an example of an XPath query for company.xml document located at company.com/info.xml. Returns the company root and all of the descendant nodes. Some examples of XPath expressions in XML documents that follow XML schema. File a company in figure 13.5. And this is basically the first one is there should be at the beginning a company element underneath of the second one is showing that the company element should have a department element underneath of it, or you want to retrieve that element. The third line basically says anywhere within that document there should be an employee element and you want it, and in particular you want it if there's an attribute on it called employee salary that is greater than 70,000. And when you find one of those, what you want back is their name. So it's essentially a way of doing a relatively complex query. The fourth one, a similar concept, without essentially the wildcard search. You're saying within the company, give me the employee that is underneath of the company that has a salary grader, and I want their name. The difference could be if you had employee objects under someplace other than company. So maybe off of company you had contractor, and maybe contractor you had employee underneath of there. They would be differentiated, and you would find them in the third one, but not in the fourth one. The fifth line is basically saying, give me back the project worker who's worked more than 20 hours on pretty much any project. Whenever you're specifying queries in XML, you've got for, let, where, order, and by, and then return. And this is when you're using XQuery. The variables are preceded with a $sign for assigning variables to a range. Where specifies additional conditions. Order by specifies order of results, and return specifies elements for retrieval. Here's an example of XQuery in motion. Honestly, you're more likely to use XPath than you are XQuery, but it can occur. Generally speaking, though, you can do about the same stuff with an XPath expression. Other languages and protocols related to XML, you have extensible style sheet languages, XSL. You have extensible style sheet languages for transformations, XSLT. Web service description language, WSDL, WSDL. You have simple object access protocols, SOAP, and you have resource description framework, RDF. All of those, except for the very first one, are very popular today. The XSL kind of went away and was supplanted by XSLT, but otherwise, pretty much all of those are still in use today. Section 13.6 is about extracting XML documents from relational databases. XML uses a hierarchical tree sort of structure. A common database model is essentially a flat tabular sort of expression. So conceptually representing ER schema, the university example follows the choices of your root or course, student, or section. This is the ER schema for the diagram of a simplified university database. 13.9 is a subset of that university database is needed for an XML document. The hierarchy tree view of courses as the root, and a potential schema for the course as the root sort of representation. And then a hierarchical tree with student as the root. So the basic idea here that you're seeing is that when you're modeling something that's inherently relational or tabular and trying to do so in a hierarchical fashion, you have to pick something to be the order in which they're presented. So in this case, you're presenting it as student, section, course. In the previous examples, it was presented in a different way. So, but because of the nature of relational databases and the nature of XML, you're going to have to kind of pick one, and you have multiple ways of essentially serializing a relational database out to XML and vice versa. But it is not as seamless as you might like because of the nature. They're two different things. You're modeling two different types of data representations. One of them is essentially a tree. The other is a series of grids. This is the schema associated with student being the root. So you have student and then various items associated with hanging off of it, student that has at a element level name, SSN, class, type, and so on, and then a sequence of sections broken down. One of the interesting things that this is being modeled is showing the essentially an element nested underneath for SSN off of a student, whereas your alternative might be to do that as an attribute, not necessarily an element. So something to think of. The breaking cycles to convert graphs into trees, sometimes you have cyclic sort of representations. You're going to basically pick something to be the root and kind of hang it off of that, so to speak. Other steps for extracting XML documents from databases is to create an SQL query for extract desired information, execute the query, restructure from a flat to a tree structure, customize query to select a single or multiple objects into the document. There's also some database systems that support the concept of you simply add something like for XML and it'll do some of that work for you. So inside of XML SQL, SQL functions for creating XML data. There's XML element, which specifies a tag or an element name that will appear in the XML results. XML forest specifies multiple element names. XML ag is for aggregating several elements, and XML root specifies the XML document with a single root element. XML, SQL, SQL functions for creating XML data continued. XML attribute creates attributes for the element of the XML root. An example is to create an XML element containing employee, last name for the employee, and employee with SSN being done as an attribute, not so much. This is showing it in an element-wise sort of notation. It's an awful lot of space to store one character, right, or one name. So to store Smith is taking 10 or 11 bytes on each end, so 20 bytes, give or take. So that's one of the challenges with this sort of approach, and that's why we may go instead to doing it more as an attribute than as an element. To retrieve multiple columns for a single row, select XML element, name, employee, XML forest, and so on, and that returns the XML you see at the bottom of the screen. To create an MXL document with last name and first name and salary of employees for department 4. And this is basically saying select XML root, XML element, name, depart 4, imps, XML aggregate, and so on. The result of that query would be something like this. So in summary, we've talked about structured, semi-structured, and unstructured data, very high level, hierarchical data models of XML standards, the language for specifying structure, and the two that we talked about were XML DDTs and XML schemas. Of those, DDT is older, schema is more current. Approaches for storing XML documents, talked about sticking it in a column in the database, sticking it on a file system, and various other sort of approaches. XPath and XQuery, two ways of querying XML to retrieve values from it, and then mapping issues of how do you figure out how to convert from relational to XML structures. And then SQL XML allows for formatting query results as XML data. So various ways to do that depending upon the vendor. And with that, we've reached the end of the chapter. As always, if you have any questions with this material, do feel free to reach out to me. That's what I'm here for. Stay safe, and we'll speak again soon.